All right, today we're going to be finishing chapter 16. This is the end of the material that will be covered on the first midterm. So we're going to just finish up sound and hearing, mostly just standing waves of sound waves, longitudinal waves, and some of their applications. So the first thing, like I said, we're going to do is standing longitudinal waves, or standing sound waves. So just like we had standing transverse waves on a string, we can also have standing longitudinal waves, although usually now we're going to be talking about a wave in a pipe, and the pipe is filled with some kind of fluid, whether it's water or air, and the wave is reflected from both ends, and we're going to have a standing wave. And just like we had standing waves that were used to create like sound and musical sounds on a string, we can obviously also use standing waves in a pipe to create music. So usually like wind instruments obviously use this to create sound. So just like with our transverse waves, we're going to have nodes and antinodes. And we also know that for sound waves, we have both displacement and pressure that we're dealing with, right? Because the wave is a pressure disturbance, and the particles in the wave are displaced along the direction of travel. So we have a displacement node in a longitudinal sound wave. And they're exactly what we know from transverse waves. So a displacement node is just a place along the wave where your actual particle is not moving. So that air particle just stays right there and it doesn't move to the left or right. Then a displacement antinode is one that will undergo the maximum displacement. So that particle, that air particle or water particle, whatever it is, will be going the maximum amplitude to the left or right. And now we also are going to have pressure nodes. So a pressure node is again one that doesn't vary. So the pressure at a pressure node stays relatively constant. And then the pressure at a pressure antinode is going to undergo the maximum compression and the maximum expansion. So it's going to be undergoing the maximum pressure differences at a pressure antinode. And these types of nodes, these displacement and pressure nodes and antinodes, are going to be connected to each other. So at a displacement node, the gas or fluid will feel the maximum and minimum pressure. So that's the maximum and minimum pressure variations at a displacement node. And then at a displacement antinode, the pressure will stay relatively constant. So a pressure node is a displacement antinode, and a pressure antinode is a displacement node. So they're basically like inverses of each other in that sense. And you can see that here in this picture, so we'll zoom in a little bit. So here we have a standing wave going through one full period, so t is equal to 0 to the period here. And these n and a denote displacement node for n and a displacement antinode for a, which is going to correspond to a pressure antinode and a pressure node since they're opposites. So you can see here let's take this first n, at a displacement node, so this particle here is not undergoing any motion. You can see that the pressure starts off, all light blue, it's all the same, and then the pressure here decreases, and then the pressure here increases, and it feels the maximum pressure here, and then it starts decreasing again. And it's the same for all of these nodes, right? So this particle, it's not moving. You can see it has minimum pressure, and then it goes up to maximum pressure, and then it's going to go back to minimum. And the same over here. While if we follow, like let's say an antinode, you can see if you kind of go on this antinode here, the pressure is staying, relatively the same color, right? It's staying the same pressure pretty much. Okay, so that's how pressure nodes and displacement nodes are connected to each other. Just remember, wherever you have a node of one is going to be an antinode of the other, and vice versa. So let's talk about standing waves specifically in a pipe. So a good example of this, or the most common example that I'm sure everyone's seen, is like a musical instrument, like all the wind instruments and an organ specifically that you'd see at like a church or something. Those are all the music in them is created by a standing wave in a pipe, a standing sound wave. So the air comes in, it has something at the bottom that pushes air into the pipe. So the air comes in, it goes into the pipes, and then usually the other end is open, and we'll talk about open and closed pipes in a minute. And then it sets up a standing wave here inside the pipe. So an organ is an example of an open pipe. So an open pipe just means that both ends of the pipe are open. And when you have two open ends, or any open end of a pipe with a standing wave, the open end is going to be an antinode, but a pressure node. And that's the case for all open ends of a pipe. It's always going to be a displacement antinode and a pressure node. And so we can think about this. Let's draw a little picture. So we have our open pipe here. It's open on both ends. So we said the end is going to be a displacement antinode. So it's going to sort of look like this. Let's just draw the minimum node, or actually, let's do it this way. So this is like my node here, and then I have an antinode and an antinode. So this is the minimum like wavelength setup that I can get on an open pipe, right? I basically just have 1/2 wavelength in here, right? That's because I want both ends to have an antinode. You can sort of think of it like an open pipe has an antinode, a displacement antinode at the end, because the air molecules at this end are moving back and forth, right? So now we can calculate the fundamental frequency of this setup, right? Because I said if we have an antinode at both ends, 1/2 wavelength is the shortest amount of wavelength I can fit in this pipe. So I said that the length of my pipe is 1/2 wavelength, right? Which means that my wavelength here is 2 times the length of the pipe. And I can find the fundamental frequency. So I know from my velocity is frequency times wavelength. So if I solve for frequency, I get v over lambda. So my fundamental frequency, so the lowest frequency I can get, is v over lambda, which is 2L. So this is going to be my fundamental frequency for an open pipe. And now I can also get other frequencies in there, right? So let's say if I draw a slightly longer pipe there, I can get something that looks more like that, right? So I still have an antinode at each end. So I've got my node there, a node there, and then this is an antinode and an antinode, and then another antinode in the middle. So I have this setup. So here, this is 1/2 wavelength, and then this is 1/2 wavelength. I didn't really draw that perfectly, but pretend those are both half wavelengths. So now I basically have the length of my pipe is 2 half wavelengths. And then I can also fit more wavelengths in here, right? I could fit 3 half wavelengths. So let's try to fit 3 half wavelengths. And it's not totally even, but it'll do. So then I have 1 node, 2 node, 3 node, and then I have an antinode there, and then 2 antinodes in the middle. So here I have a half wavelength here, a half wavelength there, and this is also a half wavelength, even though it looks a little bit longer. So now I have 3 half wavelengths here is the length of my pipe. So clearly here I can fit an integer number of half wavelengths if I need an antinode at each end. So if I want to find the corresponding frequencies for that, we know that the frequencies, whoops, that's a mistake there. I should cross that out. The frequencies are given by Fn is v over lambda. And we know that lambda, so we said L is n lambda over 2, right? The length of my pipe has to be an integer number of half wavelengths. That means that my lambda is 2L over n. So I can plug my lambda into here, and I get that the frequencies are v over 2L times n, where n is just some integer, right? So I can write that here. So these are all of the fundamental frequencies for my open pipe. So that's a pipe that's open at both ends. Here I have Fn is the frequency of the nth harmonic. V is the speed of the sound in the pipe. N is an integer corresponding to the nth harmonic. And L is just the length of the pipe. So here's a couple of pictures of an open pipe. Now be careful, because I think in your book, the way they draw the open pipe, because they're drawing it specifically the way an open pipe is made actually in an organ. It kind of like obscures the fact when you're just learning that it's an open pipe. So this is the way they draw an open pipe. I personally think that looks like it's closed at one end, but this means that it's open here because it has this little open spot, even though it looks like this end might be closed. So be careful with that. Just make sure when you look at your diagrams in the book that you're really careful about this little opening here, because that does mean it's an open pipe. So as I drew in the previous slides, for our fundamental frequency, when we have just 1/2 wavelength, this is what your wave in an open pipe will look like. We have the antinode at each end. Then the second harmonic, when n is equal to 2, you're going to have 2/2 wavelengths, so 1 full wavelength. N is equal to 2, and we have an antinode at both ends still. And then for the third harmonic, where n is equal to 3, we have 3/2 wavelengths and still an antinode at each end. So here is a diagram from the Young and Friedman book. Like I said, I think that book's a little bit better. Their diagrams, I think, are a little bit more clear with their open pipes at least. So this is, we have, n equals 2, n equals 3, and n equals 4 for an open pipe. And again, as you can see, an antinode at each end. Okay, so now we can also have, obviously, a closed pipe, right? We could close one end of it. So that's typically called a stopped pipe. Sometimes you'll also see it called a closed pipe. So that means it's open at one end so that air can get in, and then it's closed at the other end. So the open end is still a displacement antinode, which means it's a pressure node. And then the closed end is a displacement node and a pressure antinode. And so it will look like this. So let's say we have this end open, this end closed. So we want the closed end to be a displacement node and the open end to be a displacement antinode. So we can get something that looks like this, right? So this is an antinode and this is a node here. Now the reason that your closed end has to be a displacement node instead of a displacement antinode is that if your particles are moving from left to right, how can they move from left to right if the pipe is closed, right? They can't move from left to right over the boundary of the pipe, so it has to be a node at that closed end, which means it has to be a pressure antinode at this closed end as well. So now we can see that we can actually get a quarter wavelength in this closed pipe, right? So this is actually lambda over 4, right? Instead of lambda over 2 in our open pipe. So I can also try to fit some more quarter wavelengths in here, so I can draw a little longer pipe. And I still want a displacement node here, like that, and then something like that. So I've got 2 nodes and an antinode out here, and my node here and here. Okay. So here now I can see that I actually have, this is a quarter wavelength here, right? Then this is another quarter wavelength, and then this is another quarter wavelength. So I have 3 quarter wavelengths. So I can see now that my pipe that has a closed end can actually support quarter wavelengths and integer multiples of quarter wavelengths. So let's find the fundamental frequency of our closed pipe. So we know that that's going to be corresponding to 1 single quarter wavelength. So the length is lambda over 4. So that means lambda is 4 times the length of the pipe. And the frequency will be V over lambda. We'll replace lambda with 4L. So this is the fundamental frequency. So that means our fundamental frequency will be V over 4L. And that's when n is equal to 1. So this is our fundamental frequency for a closed pipe. And as you can see, we have V over 4L now, whereas before, for the open pipe, we had V over 2L for the open pipe. So we have a difference of 1/2 now. Our fundamental frequency for the closed pipe is 1/2 that of the fundamental frequency for the open pipe of the same length. Okay. So now just let's look at one more case with the closed pipe. So if we have this pipe here, let's try to put another quarter wavelength on it. Okay, so let's draw this like that. And then, again, I didn't do this perfect, but that's okay. So, okay, so we have a quarter wavelength here. Then we have, so it's like that. So we have one here, 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 right? So now I can see that my length is 5 lambda over 4. So it's 5 quarter wavelengths. So now looking back at the previous ones we had just drawn, we were able to draw 1 quarter wavelength, 3 quarter wavelengths, and now the next one is 5 quarter wavelengths. So we weren't able to draw 2 quarter wavelengths because that would just be a half a wavelength. And if we had only a half a wavelength, that would put us at a node again, right? Half a wavelength goes from, let's say, here to here. And we know that we want an antinode at the end. So that means for our closed pipe, having a node at one end and an antinode at the other end means that we can't fit half wavelengths. We need to only do quarter wavelengths, and we can only do odd integer numbers. If we were to write it, lambda is n, L is n lambda over 4. We don't want n to be even, because if n is even here, it will cancel out with the 4 and we'll get a half wavelength value. So we only want n to be odd so that we end up with those quarter length wavelengths. And now to find the fundamental frequency, the harmonics of this, again, we can just do Fn is equal to V over lambda. We know lambda is 4L over n. Put a subscript there. So Fn is V 4L then times n, right? So this is our harmonics for a closed pipe. So I'll rewrite that. I have that right here. So this is the normal mode frequencies, or our harmonics for a stopped pipe, open at one end, closed at the other. So the Fn is just our frequency of the nth harmonic, and n is only odd. So n here is an odd integer. V is the speed of the sound in the pipe, and L is the length of the pipe. So this is important because when you're talking about now the fundamental frequencies of a stopped pipe, you're never going to be talking about the second frequency or the second harmonic. You're always going to be talking about like the first, third, fifth, seventh. So you'll never see an even harmonic for a stopped pipe like this. All right, now let's do an example with this. So we have on a day when the speed of sound is 344 meters per second, the fundamental frequency of a particular stopped organ pipe is 220 hertz. So we have the fundamental frequency, so I'll write that down as F1 is 220 hertz. How long is the pipe? Okay, well, that's easy because we can just plug that into our fundamental frequency formula. And for a stopped pipe, we can just look back at our equation we just had, where n is 1, so that's just going to be V over 4L. So the fundamental frequency for a stopped pipe is V over 4L, and now we just have to solve for L, right? So we'll just do L is equal to V over 4F. So V is 344 meters per second, divided by 4 times 220. So that comes out to 0.391 meters. So our pipe is almost 0.4 meters long. And now we want to find the second overtone of this pipe has the same wavelength as the third harmonic of an open pipe. How long is the open pipe? So this one's very tricky because there's a lot of very particular wording you have to be careful of here. So let's start with the second overtone of this pipe. So that means, remember, overtone refers to the harmonic over the fundamental frequency. So the first overtone would be, we have n is equal to 1, 3, 5 for these harmonics. So the first overtone would be the first one over the fundamental, so that would be 3. So the second overtone is n equals 5, actually. So even though it's the second overtone, we're actually looking at the case where n is equal to 5. So that's confusing, or at least, tricky when you're just reading the problem, so be careful of that. So we're looking at n is equal to 5 here for our stopped pipe. So it's saying it has the same wavelength as the third harmonic of an open pipe. Okay, so let's first find the wavelength of this second overtone. So that's when n is equal to 5. And we know the length of the pipe already. And we know that the length of the pipe obeys, or the length and the wavelength are related through this formula because it can only support integer, quarter integer wavelengths. And here n is equal to 5. So we can just solve for the wavelength and figure out what the wavelength is at n is equal to 5. So the wavelength is just 4L over n. So n is equal to 5, we said, so it's 4 times the length of the pipe, which is 0.391, divided by n is 5, and that comes out to 0.313 meters. So on the second overtone, when n is equal to 5, this is the wavelength in our pipe, our closed pipe. So now we know that wavelength. So now it's saying this is the same wavelength as the third harmonic of an open pipe. So I'll add a page in here. So we have lambda is equal to 0.313, we said, for our closed pipe. So now we're looking at the third harmonic of an open pipe. So for open pipes, we have the harmonics are given by NV over 2L, and this is the third harmonic, so that just means that n is going to be equal to 3. And now we know also for open pipes that the length, the pipe can support a half integer number of wavelengths. So this is for an open pipe. So we can just plug in n is equal to 3 here. We know the wavelength is going to be the same as the 0.313, and then we can just find the length, right? Right, yeah, we just want to know how long the pipe is. So we'll just do 3 times lambda was 0.313 divided by 2, and that comes out to 0.469 meters. So that is our length of this other open pipe. All right, so now let's talk about interference. So we talked about interference a little bit in some other lectures. We can obviously also have interference for longitudinal waves. So interference is when we have 2 or more waves traveling through the same space at the same time. So standing waves were one good example of interference. But we can also obviously have interference with traveling waves, as we saw a little bit in chapter 15 already. So just for some examples, so here we have a set of speakers. So we have one speaker over here. Let's say it's outputting some sinusoidal sound wave, and this speaker is also emitting the same wave, same frequency, same amplitude, everything. So if these two speakers are emitting essentially the same sound wave, if you are the same distance away from each speaker, the waves will arrive at you in phase, right? Because they've traveled the same distance over the same time. So they'll arrive at you in phase, and you're going to end up getting constructive interference there because they're in phase. But now let's say you move half a wavelength away. Remember we said that when we have 2 waves that are 180 degrees out of phase, or they're off by half a wavelength, that's when we get destructive interference. So if we move, let's say, a little distance to the left or to the right, so that we have this distance is off by 1/2 wavelength compared to this distance, now they're going to interfere destructively. So they'll cancel each other out. The 2 waves will cancel each other out here, and you won't hear any sound here at all. And then you can also think of it this way. So here we have, let's say, a microphone. So if you have a speaker here and a speaker here, and they're placed the difference of 1 wavelength, it could be 2 wavelength or 3 wavelength, any integer number of wavelengths, they'll line up, and when they get to this microphone here, the amplitudes will add, and you'll get constructive interference, and you'll get a very loud sound. Now, if instead they're off by half a wavelength, you'll get destructive interference, and when they get to this microphone, one will be at its minimum, the other one will be at its maximum, they'll add up to 0, and you'll get no sound. So just to recap here, we have constructive interference occurs when the distance traveled by the 2 waves differs by an integer number of wavelengths, so lambda, 2 lambda, 3 lambda, and they arrive at the receiver in phase. But if the distance traveled by the 2 waves is off by half a wavelength, then they interfere destructively. So lambda over 2, 3 lambda over 2, 5 lambda over 2. And again, we only want odd numbers out here, right? Because if we had 2 lambda over 2, well, this is just equal to lambda, right? And we would get constructive interference. Same if we had 4 lambda over 2. That would just give us a difference of 2 lambda, and that again would be constructive interference. So we want this half integer difference here. So they will interfere destructively and cancel out to 0 when the path difference is this much. All right, so let's do an example to see how this works. So here we have 2 loudspeakers, A and B, that are driven by the same amplifier and emit a pure sinusoidal wave in phase. So they have the exact same sine wave that they're emitting. For what frequencies does constructive interference occur at point P? And for what frequencies does destructive interference occur? And the speed of sound is 350 here. So we have, let's just draw this. So if we're looking at it directly from above, this is point P here. This is A, this is B. This is 2 meters, 1 meter. This distance is 4 meters. So this is our diagram from above. I want to know for what frequencies does constructive interference occur here. So when will the path difference from here and here be equal to 1 full wavelength? So the first thing we should do is find the path difference. How much longer is it from B to P than from A to P? So we can just use the Pythagorean theorem for that, right? Okay, so let's do from sorry, I mislabeled this. This is A and this is B. So this is A and this is B. So let's do from A to P first. So from A to P, we're just going to use the Pythagorean theorem. And we have 2 squared plus 4 squared square root. That comes out to 4.47 meters. And then from B to P, we just have 1 squared plus 4 squared. And that comes out to 4.12 meters. So our path difference is just the difference between those two, obviously. So it's just going to be 4.47 minus 4.12, and that's equal to 0.35 meters. So our path difference is 0.35 meters. And now we know that constructive interference will occur. So we'll call our path difference D. Constructive will occur when the path difference D is equal to an integer number of wavelengths, right? And I have the velocity of sound, and I want to know what frequencies this will happen at. So I know D is 0.35. I know that the velocity is lambda times f. So I'm going to replace lambda with v over f. So let me replace this. We've got D is equal to n times v over f. And now I can just solve for f, right? Because I know n is just some integer. I know v and I know d. So let's solve for f here. So f is going to be nv over d. Let's just solve for n is equal to 1 first. So let's solve n is equal to 1 first. So we'll say that's 1. So v we said it was 350, and the path difference was 0.35. So that gives us 1,000 hertz. So this will be a frequency that there's constructive interference for, but we can also have any integer number of wavelengths, right, from over here. So you can have n is equal to 1, will give you 1,000. If you do n is equal to 2, you'll get 2,000. If you do n is equal to 3, you'll get 3,000. So basically, our answer is 1,000 hertz, or you could say n times 1,000 hertz, where n is an integer. So any of those frequencies will will give you constructive interference at this point P. Now we want to know for what frequencies does destructive interference occur. So let's add another page. All right, so, oops. So for destructive interference now, we have the same idea where our path difference, we want to be n lambda over 2, where n is an odd integer again. So we can again replace lambda with v over f. So d is n v over 2f. So this will be our path difference here. We want this. And so now let's solve for the frequency. So the frequency, we get nv over 2d. So let's solve, like we said, where n is equal to 1. We get 350 was the velocity, 2 times 0.35 was our path difference. Right, yeah, 0.35. And then this comes out to 500 hertz. So now here, our answer for the frequencies will be n times 500 hertz, where n is an odd integer, 135. So we have like 500 hertz, 1500 hertz, 2500 hertz, etc. Okay, so these type of problems come up a lot where you have like a speaker and you want to figure out either the distance where there'll be destructive or constructive interference, the frequencies, the wavelengths. These type of problems are very, very common, and you'll see them a lot. Okay, so let's move on. So now we're going to talk about beats. So let's say we have two waves that interfere. They have equal amplitude but slightly different frequencies. So what's going to happen? Well, they're going to interfere constructively and destructively with a frequency, basically. So that's called beats. So what you'll end up getting is kind of like so here we have two waves. They start off in phase, then they get out of phase, and then they come back in phase over here, and then they get out of phase again, and they're back in phase. And when they're in phase, they add up perfectly, right? So you get this maximum amplitude down here in the resulting wave. But then when they're perfectly out of phase down here, you're going to end up with total destructive interference, and it's going to be basically 0. And it's going to keep repeating. So this repeating pattern here, where it goes from maximum constructive to then destructive, maximum constructive, destructive, that's called your beat frequency. So here we have, let's say, 1 second, it says here. So we have 2 repeats of our beat pattern. So that means that the frequency of this beat frequency is 2 hertz, right? Because we have 2 cycles per second. So this is a 2 hertz beat frequency. And the beat frequency ends up just being actually the difference between the 2 frequencies, or rather the absolute value of the difference between them, because you obviously always want a positive frequency. It doesn't really make sense to have a negative frequency. So your book actually has a derivation to show that the beat frequency is really just the difference between the 2 frequencies, but I didn't really like it that much. I thought it was like not that clearly written. So I think this one from Khan Academy is a lot better. So I'll link to this if you want to see the derivation or the justification for that. This is a much better derivation. So I'll link that in the PDF. You can watch it if you're interested. And then I'm also going to put in my notes a second derivation, because obviously there's usually more than one ways to derive things. So I'll put in a second derivation that if you're interested, you can work through as well. And that second one is also in your book. Okay, so like I said, the beat frequency is just, in your book, it's just given by FA minus FB, where FA is the bigger frequency and FB is the smaller one, so that this always ends up being positive. You could also, if you want to just write it as, FA minus FB, absolute value, and then you don't have to worry about which one is bigger or smaller. You just take the absolute value, so you always get a positive number. That's totally legitimate too. So just one thing to be careful of when you're doing beat frequencies is that, let's say you know the beat frequency and you know the frequency of one of the waves involved. So let's say one of the waves, F1 is like 10 hertz, and they tell you that the beat frequency is 2 hertz. you only know the difference between the two frequencies. So you don't know if the other frequency is 12 or 8. So you have to just be a little bit careful with that. The beat frequency only gives you the difference. You don't know which frequency is actually the larger one or not, if this is the only information you have here. Okay, so now we're going to talk about something very important, which is called the Doppler effect. So the Doppler effect affects all kinds of waves and sources of waves that are moving relative to each other. So if you're listening to something and the source of some sound, like usually like an ambulance or a police siren, if you're in your car and the siren is getting closer to you, you start hearing a higher frequency as it gets closer, right? And then as it passes you and goes away, you start hearing a lower frequency. And this is true also if the siren was still and it was not moving and you were moving closer to it, you would hear a higher frequency as you got closer and then a lower frequency as you got farther away. So this actually affects like all kinds of waves. We're going to see when we do electromagnetic waves, there's also a Doppler effect for electromagnetic waves. And so the reason that this happens is, let's say you're here and there's a car, some kind of siren that's like making music here. It's emitting sound waves like this, right? So they're equally spaced here. If you start moving, let's say in this direction, with some speed v, it's going to look to you like this is actually emitting frequency at a higher rate than it really is, right? Because it's emitting some steady frequency, and now you're moving like closer to it. So instead of, let's say, only hearing like 1 cycle per second if both of you were standing still, if you are moving towards the source, you might now hear 2 cycles per second or 3 cycles per second because you're moving. So you'll hear a higher frequency. And the same as if you went, if you were going in the other direction, if you decide to go that way, instead of only hearing 1 cycle per second, you might hear instead half a cycle per second because you're as you're moving away, the sound waves kind of have to catch up to you as well. So you'll hear a lower frequency. All right, so let's see how this works for a stationary source and a moving listener. So you're here and you're moving this way, and then someone else is here. And let's say they have like some kind of music thing you are moving, the listener is moving with some speed VL. The source is standing still at 0. And now the frequency that the listener will hear, just like always, we have the frequency is V over lambda, right? So now here, if you're moving towards the source, so if this little guy is moving towards the source, the speed of sound will seem like the regular speed of sound plus the velocity that the listener is moving with, right? Because it's going to seem like it's actually moving faster. So this velocity here will seem like it's V plus VL, right? And now the wavelength that the source is emitting is just the usual V over Fs, where Fs is the frequency that the source is emitting, and Fl is the frequency that the listener is hearing. So let's rewrite that. So we have V plus VL over V, F source. And we can see here that this is a higher frequency, right? So here we see that FL is bigger than Fs, which is what we'd expect, because if you are moving towards the source, you should start hearing a higher frequency. So since here our numerator is bigger than the denominator, that means that FL is going to be bigger than Fs. So this worked out the way we expected it to, and this is our Doppler shift for when the listener is moving towards the source, and the source is sitting still. Now if instead, let's say the listener was actually moving away, so if the listener was moving this way instead, it would look like the waves are actually slower, right? So here, all you would have to do is have V minus VL. Everything else would be the same, but this velocity here would look like it's less because you're moving away from the source. And now here you can see FL is going to be less than VS, which is what we would expect, because if you're moving away from the source, you expect a lower frequency. And that's because the numerator here will be less than the denominator if we subtract VL. All right, now let's look if the source and the listener are both moving. So here we have them both moving. So our source is moving away, and our listener is also moving towards the source. So here you can see that the wavelengths actually look a little bit different if your source is moving as well, right? Because as your source starts moving, the source emits some waves with a wavelength, right? But as the wavefront starts moving, the source is also kind of moving with the wavelength. So it's going to actually sort of pile up wavelengths and make the wavelength look smaller than it would be if it was standing still. So the wavelengths in front actually look shorter, and the wavelengths behind look longer, because now you emit a wave and you move away from it. So it's going to look like you have a bigger wavelength than you really do if you were sitting still. And so we can quantify this by saying, okay, let's say the wave in front normally would just look like V over Fs, where Fs is the frequency of the source. But now in front, it's going to be shorter, so you're going to subtract that little distance that the source is moving, right? So this here is some distance, right? That the distance that the source traveled. So this distance is how far did the source move in some time, right? So distance is equal to velocity times time. So I'm going to figure out how far did the source move in one period, right? So imagine it. So each time it emits, one of these waves, that's every period, right? So the velocity of the source, because we want to know how far did he move. The velocity of the source times the period. How far did he move in one full cycle when he emitted the next wave? And we know that the period is 1 over the frequency. So this is Vs over the frequency of the source, right? So we can just replace, so this distance is just Vs over Fs. So it's the, so here it's the velocity of the wave itself traveling minus the velocity of the source, because it's going to give you a slightly shorter wavelength. And now behind, we can do the same thing behind, where we're going to have lambda behind is V over Fs, where remember, this V is the velocity of the wave, and this Vs is the velocity of the source. So those are two different velocities. So we have the velocity of the wave itself. And now here, the wavelength is going to look bigger, right? So as the source moves away, the wavelength is going to look bigger. So we're going to add the same thing, Vs over Fs. So now we can write the Doppler shift for the case where both the listener and the source are moving. So I can just take this, and I'm going to rewrite it a little bit more compactly as V plus minus V source over F source. So I just rewrote what we had there with a plus or minus, depending on whether you're looking at in front or behind of the source. So now I can do the exact same thing that I did in the previous examples for the Doppler shift. So now I can just write the frequency that the listener hears is going to be V plus VL, as we had before, over the wavelength that the listener observes now. So that's going to be this, depending on how they're moving relative to each other. And we're going to see examples of this in a second. So I'm just going to replace the lambda down here with this. So this will become V plus minus Vs Fs. And I can also put a minus here depending on if the listener is moving towards or away from the source. So this now is my Doppler effect for any case, no matter how the listener and mover are moving relative to each other. These plus minuses in here will cover everything. So I rewrote it here, so I should actually just add in the plus minus. So this is the Doppler shift for any scenario you have, no matter how they're moving, the listener and the source are moving relative to each other. So FL is the frequency heard by the listener. FV is the velocity of the listener. Fs is the frequency emitted by the source. Vs is the velocity of the source. And V is the speed of sound in the medium. So the way that I personally like solving these Doppler shift problems, instead of memorizing like a bunch of different formulas with pluses and minuses depending on if the listener is moving towards the source or away, blah, blah, I just figure out like, okay, if they're moving towards each other, they should hear an increase in frequency, right? If they're moving away, they should hear a decrease. So that alone will allow you to figure out what you need to add and what you need to subtract, depending on if you just know if FL should be greater than or less than FS. Okay, so let's do some examples to see how this works. So here we have a police siren emits a sinusoidal wave with frequency 300 hertz, and the speed of sound in air is 340 meters per second. What is the wavelength of the waves if the car is at rest? So let's do that first. So that's easy. So we have just our car here. So we have our little card here, and it's at rest. So we have the velocity is lambda times f, and we want to find the wavelength. So the wavelength will just be the velocity divided by the frequency. The velocity, they say, is 340, and the frequency we know is 300. So that will just give us 1.13 meters. So this is the wavelength when the car is at rest. And then we want to find the wavelength in front and behind the car if it's moving at 30 meters per second. So lambda in front, we said will just be the original V over F, right? But then we're going to subtract the velocity of the source and the frequency of the source, right? Because these wavelengths we expect to be shorter, since in front they're kind of going to pile up as the car drives. So here, this is just V minus Vs over Fs, because it's the frequency of the source. So this is the velocity of the waves in air is 340 minus 30 is the velocity of the source, divided by the frequency of the source is 300, and this gives us 1.03 meters. So this is what we would expect because this wavelength is shorter than the wavelength when it's standing still. So now the wavelength behind, we're going to have the same thing where it's V, the velocity in air divided by the frequency of the source. But now it's going to be plus because we expect the wavelength to look longer behind the car. So now that's going to be plus Vs over Fs. So we have V plus Vs over Fs. So we have 340 plus 30 divided by 300, and that gives us 1.23 meters. And that's again what we expect because this is longer than the at rest wavelength. All right, so now, same problem. If a person is standing at rest behind the car, so now we have the police car here. We have a person standing at rest behind it. What frequencies does that person hear? So the car we said is moving at 30 meters per second, so it's moving this way at 30 meters per second. And our listener is standing still, and the frequency, so this is Vs, and the frequency of our source we said was 300 hertz. So we're obviously just going to use the Doppler shift where we have FL is V plus minus VL, V plus minus Vs, Fs. Okay, so we know right away that our listener is standing still, right? So this velocity is 0. The velocity of the listener is 0. The velocity of the police car, the source, is obviously not 0. It's 30 meters per second. So should it be plus or minus? Well, we expect, since they're moving away from each other, right? The siren, the police car is moving away from the person. We expect FL to be less than Vs. So if we expect the FL to be less than Fs, that means this has to be a positive down here, right? Because we have to have V divided by some bigger number because we need to multiply the frequency of the source by a number less than 1 in order to have FL less than FS. So this will be a plus. So we're going to have FL is V over V plus V source, F source, and that is the velocity of sound. They said in this was 340 divided by 340 plus 30 times the frequency is 300, and this gives us 276 hertz. So this is what we expect. The frequency that the listener hears is less than the frequency that the source is outputting, so that makes sense. Okay, now let's say if the police car is at rest and the person is driving away at 30 meters per second, what frequency does that person hear? So now we have the police car here is at rest, so this is the velocity of our source is 0. And then we have another car here that's moving away at 30 meters per second, so this is the velocity of our listener. The frequency of our source is still 300. What frequency does the person in this car hear now? So let's write down our Doppler shift. Oops, this is a L. Okay, so now we know right away that our V source is 0, right? So that's 0. And again, we expect FL to be less than FS, right? The frequency that our listener hears is going to be less than the frequency of the source because he's moving away from the source. So that means we need this, this sign here to be negative, right? Because we want, again, this factor to be less than 1 so that FL can be less than FS. So that means we need to subtract our VL. So we have FL is equal to V minus VL over V. So that is 340 minus 30 divided by 340 is, times 300. And that comes out to 274 hertz. So again, our frequency is less than the frequency of the source that the source is outputting, which we expect. Now let's say that they're both moving. So now let's say that the police car and the listener are both moving. So our police car is in front and he's moving at 45 meters per second. So the velocity of our source is 45 meters per second. The listener is behind him moving at 15 meters per second. What frequency does the listener hear now? Well, let's see. So we're going to write our Doppler FL V plus VL over V plus minus VS over FS. So do we expect him to hear a higher frequency or a lower frequency? Well, the police car is moving faster than our listener, so as time goes on, the police car is going to get further and further away. So you should expect to hear actually a decrease in frequency because the police car is getting further away. So again, we expect FL to be less than FS. So again, that means that we want the number right here to be less than 1 so that FL will be less than FS. And here we have the listener is moving at 15 and the police car is moving at 45. So both of these signs here are going to be positive because our listener is moving towards the source and that is associated with a positive sign there. And then our source is also moving in that same direction. So we're going to get two positive signs. So we're going to have FL is V plus VL over V plus VS, FS. So that gives us 340 plus 15 over 340 plus 45 times the frequency was 300. So this gives us 277 hertz. So again, we get an answer that we expect and that the frequency that the listener hears is smaller than the frequency that the source is actually emitting. Okay, so this is everything for chapter 16. Um, Make sure that you study the Doppler shift a lot, especially the positive and negatives, because I know that's very easy to get tripped up on. And when I post my notes to Canvas, I'll post some more, like I'll write out the sign conventions a little bit nicer, so that you can at least reference those. But do a lot of Doppler shift problems. A Doppler shift problem will definitely come up on the midterm, so definitely make sure that you're comfortable with that. But okay, so that's it for chapter 16, and I will have a review for you guys next week.